Hello there, and welcome to the Sleep Porch. Tonight, we are drifting back to the very beginning of everything we know. Long before stars burned or galaxies spun, before time had a rhythm or space had a shape, the universe began its long and mysterious journey. The Big Bang is not just a single moment frozen in the past. If this content interests you, please take a moment to like the video and subscribe to the channel. Your support motivates us to continue creating more meaningful videos. It is an unfolding story that is still written across the night sky, carried by ancient light and echoed in the deep structures of the cosmos. This is not just an exploration of our origins, but of our connections. Also, the atoms within you share a lineage with the earliest moments of the universe. The laws that shaped the first galaxies also shape the world around you in this very moment.
As we explore this vast beginning, we will move through mind-bending discoveries while revealing mysteries that are still beyond the reach of science. If you enjoy these gentle journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. For now, there is nothing you need to do but relax. Allow your body to soften and your breathing to slow. And let the day fade away as we explore the origins of the universe together. Let's begin. The Big Bang doesn't describe a bang at all. It describes our universe expanding from an ultra-hot beginning. What gives this idea such force is that it isn't a legend or a hunch. It is a model that ties together many very different clues into a single, consistent account. When we look outward, we see that light from faraway galaxies is shifted toward longer wavelengths, and that shift increases the farther away they are. This pattern aligns with a universe that is expanding. When we measure the faint, leftover glow filling the sky, it matches what a universe that was once much hotter should have left behind. When we examine the amounts of the lightest elements in ancient gas, those values line up with what a young, hot cosmos would have produced. Taken together, these strands of evidence turn a daring origin story into something that can be tested. The Big Bang is not merely a starting point. It is a framework that continues to be checked against what we observe in the sky. It was not an explosion happening inside space. It was the expansion of space itself. In a normal explosion, fragments rush outward into an already existing room. This beginning was stranger than that. The room itself expanded. That distinction helps explain why there is no special center to indicate and no edge that one could travel toward. Every region sees other distant regions moving away because the distance between them is being stretched. This also explains why very remote galaxies can recede faster than the speed of light without breaking relativity. Nothing is outrunning light through space. Instead, the scale of space between faraway places is changing. This idea also changes how we picture the early universe. It was not matter bursting from a single spot. It was an everywhere that was once smaller, hotter, and denser, then expanded and cooled as a whole. The universe began as a smooth fireball, then grew lumpy. At first, the cosmos was amazingly even, with energy and particles spread almost uniformly. If it had stayed perfectly smooth, nothing interesting would ever have formed. Gravity needs tiny differences to amplify. The remarkable twist is that the early universe did have small variations,
and we can still see their fingerprints. They were slight, yet they were enough. Over immense time, denser regions tugged a little harder, pulled in more material, and became denser still.
That runaway process built structure from almost nothing. The lumps became gas clouds. The clouds became the first stars. The stars gathered into galaxies. The galaxies gathered into clusters. When you look at the night sky, you are seeing a grown-up version of faint, early irregularities magnified by gravity into a universe full of shape. The oldest light we can see still fills all directions today. This light began its journey when the universe finally cooled enough for electrons to settle into atoms. Before that moment, free electrons scattered light constantly, so the cosmos was like a glowing fog you could not see through. Once atoms formed, light could travel long distances without being knocked around. Those ancient photons have been crossing space ever since, and they still arrive at Earth from every direction. Time has stretched their wavelengths. So what began as hot, visible, or infrared light now reaches us mostly as microwaves. By studying this all-sky glow, scientists read a snapshot of the universe when it was still young. It is not a picture of stars or galaxies. It is a picture from before they existed, and it lets us test ideas about how the early universe behaved. That afterglow is colder than deep space, yet it is everywhere. Today, that ancient background glow has cooled to only a few degrees above absolute zero. Empty space is often described as cold, but this faint radiation sets a real temperature floor that permeates the universe. It is not bright to your eyes, yet sensitive instruments can measure it with astonishing precision. It also shows up in a surprising place. A small part of the static you see on an untuned television has the same cosmic origin, arriving after a journey that began long before the Earth formed. The afterglow is also incredibly uniform, which is a clue that the early universe was well mixed. At the same time, it contains tiny variations but act like a map of primordial conditions. In that sense, the coldness is not emptiness, it is information. For a short time, the universe was hotter than any star core. The hottest stellar corals reached tens of millions of degrees. In the early universe, temperatures were vastly higher. At such extremes, atoms cannot exist. Even nuclei cannot survive. Matter becomes a sting soup of fundamental particles and radiation interacting constantly. In that environment, familiar distinctions blur. Energy turns into particle pairs, and particle pairs turn back into energy. The cosmos is not a collection of objects. It is a changing state of physics itself. As expansion continued, the temperature fell, and the menu of possible particles changed with it. Some species became rare, others froze out and remained. This is why early conditions matter so much. The particle physics of those moments helped decide what ingredients the later universe would have available. When we build high-energy experiments on Earth, we are not just smashing particles. We are briefly recreating echoes of that primordial heat. In the first minutes, the cosmos forged most of its helium. Helium is often associated with stars, yet a large fraction of it was made before the first star ever ignited. As the universe cooled from its earliest heat, photons and neutrons began to stick together. This was a narrow window. It was hot enough for nuclear reactions, yet cooling quickly. Within minutes, most free neutrons were locked into helium nuclei, because helium is especially stable. That is why about a quarter of the normal matter mass in the universe is helium today. Even in places with few generations of stars, the same early process also created small amounts of deuterium and a trace of lithium. These abundances are not random. They depend on the density of ordinary matter in the young universe.
That is why measuring light elements in ancient gas can test the Big Bang story with impressive accuracy. Every atom in your body traces back to early cosmic history. Some of your atoms have a lineage that starts in the first minutes when hydrogen and helium became the universe's first long-lived building blocks. Many others arrived later, made inside stars that lived, aged, and transformed. Carbon that anchors your biology formed in stellar furnaces. Oxygen was built in massive stars and scattered when those stars died. Iron that carries oxygen in your blood was forged in violent stellar endings. Even rarer elements like gold and jewelry are linked to extraordinary events where atomic nuclei are blasted together under intense conditions. None of these stories replace the earlier one. They layer on top of it. The early universe set the stage and provided the raw simplicity. Later cosmic generations added complexity. When you hear that you are made of star stuff, it is true. And it is also only the middle chapters of a longer origin. Tiny early ripples grew into galaxies, clusters, and cosmic webs. Those early variations were not just random bumps. They had patterns that modern surveys can still detect. Ordinary matter alone would have struggled to clump quickly enough because radiation pressure resisted collapse in the early era. An invisible component that interacts mainly through gravity provided extra pull and helped structure form earlier and faster. Over time, matter streamed into denser regions and vast filaments grew between enormous voids. Galaxies formed along these filaments like beads on threads, and clusters assembled where threads intersected. This large-scale structure is one of the most striking outcomes of simple gravity acting for a long time on small beginnings. It also functions as a vast laboratory. By charting where galaxies lie and how their arrangement changes with distance, researchers can test how rapidly the universe expanded and how strongly gravity guided its development over cosmic time. Our very existence relies on a slight imbalance between matter and antimatter. In the hot, early universe, energy produced matter and antimatter in paired form, and those pairs could annihilate back into light. If the cosmos had created perfectly equal amounts, nearly everything would have wiped itself out, leaving behind a thin sea of radiation and almost nothing more. Instead, for reasons still under study, there was a minute surplus of matter. After most annihilations were complete, that small remainder became the substance of stars, planets, and people. This stands as one of the deepest, unresolved questions in cosmology because it connects the largest scales of the universe to particle physics. The universe requires processes that treat matter and antimatter just slightly differently. And it requires conditions where that difference can have real consequences. Experiments study subtle symmetry violations, while cosmologists look for clues in the sky. The fact that anything solid exists at all is evidence that the early universe played favorites just a little. Timekeeping for the universe uses age measured by cosmic expansion. Instead of counting birthdays, cosmologists read the universe like a clock built into space itself. They measure how fast galaxies separate at different distances and how that rate has changed over time. Expansion leaves multiple records. It stretches light from distant galaxies, and it also sets the size of patterns imprinted in the early universe that we can still measure today. When those independent measurements agree, they pin down a consistent timeline for cosmic history. That is how we can say the universe has an age at all, even though nobody was there to watch it begin. This approach is also why debates about the exact expansion rate matter so much. A small change today reshapes the inferred past, and it can hint that something important is missing from our current picture. The early universe was so dense that light could not travel freely. Imagine trying to see through a storm where every beam is instantly scattered. In the earliest eras, space was filled with charged particles moving fast, and photons kept colliding with them. Light existed, but it could not carry an image across any meaningful distance. The whole universe acted like an opaque, glowing fog. This is a crucial detail because it means our cosmic story has a natural visibility limit. We cannot see earlier than the moment when conditions changed and light finally started moving in long, straight paths. Before that, the universe was not dark.
It was too bright, too hot, and too crowded for transparency.
That early opacity also shaped what could form. With radiation tightly coupled to matter, pressure fought gravity, and growth was forced to wait for the universe to cool and thin. When atoms first formed, the universe suddenly became transparent. There was a time when the cosmos changed character, almost like a curtain lifting. As temperatures dropped, electrons could finally stay bound to nuclei instead of being torn away by energetic collisions. Once most matter became neutral, photons stopped bouncing constantly and began to stream through space. That transition released the oldest light we can observe. It also set the universe on a new path, because neutral gas behaves differently from an ionized plasma. Pressure dropped, cooling became more effective, and gravity had a clearer run at gathering matter into denser regions. This is one of those moments where a change in microscopic behavior rewrote the fate of everything on the largest scales. It is also why the early universe can be studied like a fossil. A single transition left a whole sky of information, and we can still map it with precision. Hydrogen formed first, then helium, then a whisper of lithium. That simple chemical starting point shaped the universe's personality for a long time. With almost no heavier elements available, early gas could not cool easily, and cooling matters because it helps clouds collapse to form stars. Hydrogen and helium have limited ways to shed energy, so the first star-forming regions likely had to be massive, patient, and extreme. Lithium existed in tiny amounts, but it was far too rare to change the chemistry in a big way. This is why the first generations of cosmic objects were probably very different from familiar stars today.
Later on, once stellar processes began enriching space with heavier elements, cooling became more efficient, and smaller stars could form. In a sense, the early universe began with a very limited toolkit, and the complexity we see now was earned slowly through cosmic time and repeated cycles of birth and destruction. The first atomic nuclei formed before any stars ever existed. It is strange to realize that nuclear physics happened on a universe-wide scale before the first pinprick of starlight. In those earliest minutes, the entire cosmos was hot enough for nuclear reactions, and it was also expanding fast enough to shut them down. That combination matters. Stars can keep fusing for millions or billions of years because gravity holds their cores hot and dense. The young universe had no such confinement. It cooled as it expanded, and it moved past the conditions needed for fusion. So the first nuclei were created in a brief global burst of nuclear assembly. And then, the opportunity vanished. This early chapter set the baseline composition of the universe, and it established the raw material from which later stars would build everything else.
It is an origin story written in physics rather than flames. Neutrinos flooded the universe long before the first atoms formed. Neutrinos are real particles, and they interact so weakly that they can pass through a planet with hardly a whisper of contact. In the early universe, they were produced in enormous numbers, and then they slipped away from the rest of matter when the cosmos was still extremely young. If a background sea of these ancient neutrinos still fills space today, it would be a relic even older than the earliest light we can see. Detecting it directly is brutally difficult because neutrinos rarely interact with anything. Still, their presence matters. They affect how quickly the universe expanded in its earliest moments, and they leave subtle fingerprints on the growth of structure over time. In a way, the universe has been filled with invisible travelers since the beginning, carrying information from eras we cannot observe with light. Most matter today is not atoms, it is invisible, dark matter. When astronomers weigh galaxies by how fast their stars orbit, the numbers do not match what we can see. Something unseen adds extra gravity. The same mystery appears in galaxy clusters, where visible matter is not enough to hold the system together. It also appears when mass bends light from background galaxies, which lets us map gravity directly without relying on starlight at all. Again and again, the maps show more mass than the atoms can provide. Dark matter is the name we give to that missing gravitational ingredient. It does not seem to shine, and it does not seem to absorb light in the usual way.
Yet it shapes the universe on enormous scales.
One of the most exciting possibilities in modern science is that dark matter could be a new kind of particle, and discovering it would expand physics beyond the familiar catalog. Dark matter shaped the first structures by pulling gas into wells. Long before there were shining galaxies, dark matter began to gather into clumps under gravity. Those clumps formed a scaffold that ordinary gas could fall into. Gas alone would have had a harder time settling early on because radiation pressure pushed back. Dark matter did not feel that pressure, so it could start building structure earlier. Over time, gas collected inside these invisible halos, cooled where it could, and eventually ignited the first stars. In this picture, the first galaxies were born inside gravitational wells that were already there, and the bright parts we see today are like lanterns hanging inside much larger, dark structures.
Computer simulations show this process in vivid detail. They grow a cosmic web from tiny beginnings, and they produce filamentary networks that look remarkably like what surveys of real galaxies reveal. It is a powerful example of how the unseen can leave visible architecture. Dark energy makes cosmic expansion speed up, not slow down. For a long time, many people expected gravity to gradually slow the expansion like a ball tossed upward. Then, observations of distant exploding stars suggested the opposite. The expansion has been accelerating for the last several billion years. Dark energy is the name given to whatever is driving that acceleration. It might be a constant energy of space itself, or it might be something that evolves over time. Either way, it changes the universe's long-term future. If acceleration continues, distant galaxies will slip beyond a cosmic horizon and become unreachable. Even in principle, that does not mean the universe ends. It means the visible universe becomes smaller from our perspective as time goes on. This discovery also connects the very large with the very small, because the simplest explanation involves vacuum energy. And vacuum energy is tied to quantum ideas that are still being wrestled into a complete comp theory. Galaxies are racing apart because space between them keeps stretching. Expansion shows up as a relationship between distance and speed, and it makes the cosmos feel alive with motion, even when galaxies are not firing rockets. As the scale of the universe increases, light traveling through space gets stretched too. and its color shifts toward the red. That is why redshift is such a central tool in cosmology. It is not only a sign that things are far away, it is also a sign that the universe changed while the light was in transit. Yet, this stretching has limits in everyday life. Your body does not expand and your solar system does not swell, because gravity and other forces hold bound structures together. Expansion is most obvious across the immense spaces between galaxy groups, where nothing strong enough resists the widening of distance. Thinking this way can reframe the night sky. It is not a fixed dome of lights. It is a record of changing geometry. We see distant galaxies as they were, not as they are now. When a telescope catches the light of a faraway galaxy, it is catching a message that has been traveling for a very long time. That means the image is history, not a live view. Some of the faint smudges in deep space photographs are galaxies from an era when the universe was still young, when stars were forming fast and shapes were rougher and more chaotic. This is why astronomy is so different from most sciences. You cannot bring a galaxy into a lab. So the universe brings you its past instead. It also means the sky is layered like a timeline. Nearby galaxies show later chapters, and the most distant ones show earlier chapters. With newer instruments, we are pushing that time window farther back. And each stage shows how the familiar universe we see today came to feel like home. The observable universe has a horizon because light has had limited time to travel. There is a limit to what we are able to observe, and it exists for a straightforward reason. The universe has a finite age. As a result, light has only had a finite amount of time to reach us from beyond a certain distance. Even if something exists out there, its light simply has not arrived yet. This produces a natural cosmic horizon. It is not a physical wall in space, and it is not the edge of the entire universe. It is an edge of information for us. The size of this observable region depends on how expansion played out over time, because expansion determines how far light can move while space itself is stretching. This is why cosmology feels like detective work, governed by strict rules. The universe provides us with a sphere of evidence, and within that sphere, we must rebuild the story using light, gravity, and the faintest patterns that survived from earlier epochs. Some regions will never be observed, because expansion carries them away faster than their light can reach us. Even if you wait forever, there are places whose signals will never reach us. This is not because they are hidden behind dust or blocked by something in the way. It is because space can expand in such a way that the distance between us and those regions grows too quickly for their light to make progress toward us. In a universe with accelerated expansion, there can be an event horizon that is different from the horizon set by the universe's age. It divides what can ever influence us from what cannot. That idea is both unsettling and thrilling. It suggests the universe may contain vast realms that are real, yet permanently disconnected from our future observations. It also means the cosmos has an element of built-in mystery. Some chapters exist, but they cannot become part of our evidence. They remain beyond reach, not by technology, but by geometry. The early universe behaved like a plasma, not a gas. A gas is made of neutral atoms that mostly ignore distant electric forces. The early universe was different. It was so hot that electrons were not bound to nuclei. So matter was made of charged particles, moving in a bright sea of radiation. That state is called a plasma, and it has a personality of its own. Electric and magnetic forces matter. Waves can travel through it,
and light does not pass through cleanly because it keeps scattering off free electrons. If you have seen the glow of a neon sign, you have seen a tiny example of a plasma at work. The early universe was like that, but on the scale of everything. This matters because the plasma stage sets the initial conditions for later structure. It determined how pressure pushed back against gravity, how energy flowed, and how the universe cooled into the calmer atomic era that followed. The first sound waves in plasma left patterns in galaxies. In the young universe, pressure and gravity played a dramatic tug-of-war. Gravity tried to pull matter into denser regions, while radiation pressure pushed outward and resisted collapse. That push and pull launched waves through the hot plasma, and they behaved like sound does in air, except the medium was a glowing mixture of particles and light. These waves traveled outward from early dense regions, and they carried matter with them as they went. Then, the universe cooled enough for light to decouple from matter, and the waves effectively froze in place. Their motion stopped being driven by radiation, and the pattern they had carved into matter remained. Much later, when galaxies formed, they inherited that ancient imprint. So when astronomers map where galaxies prefer to be, they are not only seeing the work of gravity over billions of years, they are also seeing a faint echo of pressure waves from a time before any stars existed. Those fossil sound waves are called baryon acoustic oscillations. The name sounds technical, but the idea is beautifully concrete. Ordinary matter, which physicists called baryonic matter, participated in those early pressure waves. The waves left a preferred separation scale in how matter was distributed. Much later, that scale shows up as a slight tendency for galaxies to be found a particular distance apart, more often than random chance would predict. Surveys that measure millions of galaxy positions can detect this subtle preference, and it becomes a powerful tool. It acts like a standard ruler placed in the early universe. When we observe that ruler at different distances, we are also observing it at different times in cosmic history. That let scientists infer how the universe expanded across eras. It is remarkable that a pressure wave in a primordial plasma can become a measuring stick for the geometry of space billions of years later. Cosmic background spots reveal temperature differences of mere micro amounts. The ancient sky glow is extremely uniform, yet it is not perfectly smooth. When satellites map it, they find tiny warmer and cooler regions spread across the whole sky. The differences are so small that they are measured in millionths of a degree, but they carry enormous meaning. They show that the early universe had slight variations in density and motion, which later shaped what could grow. These spots also encode a wealth of information about the contents of the cosmos. Their sizes and contrast depend on how much ordinary matter there was, how much invisible matter influenced gravity, and how radiation interacted with everything at the time. It is like reading a barcode stamped onto the universe when it was still young. The pattern is subtle, but it is consistent and measurable. From that faint modeling, scientists extract a detailed portrait of the universe's early conditions. Those tiny differences became the seeds of all later structure. A small advantage, given enough time, can become a kingdom. In the early universe, slightly denser regions had slightly stronger gravity. That extra pull helped them gather more matter, which made them denser still, which increased their pull again. Over vast time, this feedback turned small fluctuations into large structures. The process did not happen smoothly everywhere. Some regions became the crowded neighborhoods of the cosmos, and others emptied into enormous voids. Along the way, gas fell inward, heated up, cooled down, and eventually formed stars and galaxies inside larger gravitational environments. This is why the universe looks textured rather than uniform. It also explains why structure is such a sensitive test of cosmology. If you change the early seeds, you change the later landscape. Modern simulations begin with tiny fluctuations and let gravity do the rest. When the results resemble real galaxy maps, it feels like watching the universe assemble itself again. The universe has a nearly perfect black body spectrum in its afterglow. When you spread the cosmic afterglow into its colors, it matches an ideal thermal curve with extraordinary precision. A black body spectrum is what you get from something that has been in near-perfect thermal balance, like a hot object glowing smoothly rather than producing sharp lines. That is exactly what the early universe should have produced, because matter and radiation were tightly mixed and constantly interacting. The stunning part is how clean the result is. Real systems often show distortions, impurities, or extra features. The cosmic background spectrum is almost immaculate. Instruments designed to measure it treated the sky like a laboratory source, and the match to a thermal curve became one of the most persuasive pieces of evidence for a hot, dense, early phase. It is as if the universe kept a receipt from its earliest era. And that receipt still checks out when we test it today. That spectrum is one of the strongest clues for a hot beginning. A thermal spectrum of that quality is hard to fake. Many alternative origin ideas might produce radiation, but producing a sky-filling glow with the right shape, the right smoothness, and the right temperature today is a tall order.
The hot beginning picture predicted that such a relic should exist, and it predicted the form it should take, once expansion stretched it into longer wavelengths. When measurements confirmed both the existence and the shape, it tied the model to a specific, testable outcome. It is also a clue that reaches deeper than a single observation. The same early conditions that create a thermal background also create the environment needed for the first light element nuclei to form, and they set the stage for later structure to grow. So the spectrum does not stand alone. It fits into a wider story where multiple independent clues converge on the same conclusion. That convergence is what turns an idea into a compelling cosmic narrative. In the early universe, protons and electrons could not stay together. Heat was not just warmth back then. It was a constant barrage of energetic light. Anytime an electron tried to settle near a proton, a high-energy photon would strike and knock it free again. The universe behaved like a restless ocean of charged particles, and electric forces mattered everywhere. This kept matter and light tightly linked, like dancers who could not let go. It also meant the universe did not have atoms, chemistry, or the kinds of stable structures we take for granted. Everything was raw, reactive, and fast. As expansion continued, the temperature dropped, and the relentless breakups began to fail. That shift opened the door to a new era where neutral atoms could finally exist, and light could start traveling longer distances. It is amazing that the possibility of calm, stable matter depended on the universe cooling just enough. Recombination is when electrons finally settled into stable atoms. This moment was less like a single spark and more like a grand settling of the cosmos. As the universe cooled, collisions became gentler, and electrons could finally remain bound to nuclei for long stretches of time. The result was a dramatic change in behavior.
Neutral atoms do not scatter light as aggressively as free electrons do. So, the fog of the early universe began to clear. Matter also began to act more like a gas than a plasma, and that changed how it could clump and cool. You can think of it as the universe switching from a loud, crowded room to a quieter space where signals could travel. The light released around this transition became the oldest light we can observe today. It is not a message written in words. It is a record written in temperature patterns and polarization. And it tells us what conditions were like when the universe first became transparent. Before stars, the universe entered a long, cosmic dark age. After the first neutral atoms formed and the oldest visible light was released, the universe did not immediately blaze with stars. Instead, it entered an era with no new starlight at all. Space was filled with hydrogen and helium gas, and gravity was slowly gathering it into denser regions, but nothing had ignited yet. It was dark in the everyday sense, even though the universe still held a faint background glow that kept cooling as space expanded. This long pause matters because it was a time of preparation. Density peaks were growing, invisible scaffolds were deepening, and the first star-forming clouds were slowly taking shape. The Dark Age is hard to observe directly, which makes it one of the most tempting frontiers in astronomy. When we learn to detect signals from this era, we will be listening to the universe before its first lights turned on. The first stars ended the Dark Age by flooding space with ultraviolet light. The first stars were not just new objects in space. They acted like cosmic switches being flipped.
When they ignited, their powerful ultraviolet light started to alter the surrounding universe. That radiation was able to tear electrons away from hydrogen atoms, returning neutral gas to an ionized state in a process that expanded outward over time. This change is known as reionization, and it transformed both how the universe appeared and how it behaved. These early stars also began forging heavier elements in their cores, then dispersing some of that material when they died. In that sense, they served as both beacons of light and chemical trailblazers. Their radiation carved out bubbles in the surrounding gas, and those bubbles expanded and merged until much of the universe was influenced. It is difficult to overstate how dramatic this moment was. For a long stretch, the cosmos lingered in darkness, and then the first stars started rewriting the transparency and chemistry of space itself. Early stars likely formed from almost pure hydrogen and helium. Lacking heavier elements, star formation in those times posed a very different kind of challenge. Metals, in the astronomy sense, help gas cool by letting it radiate energy away. With almost none available, primordial gas had fewer ways to shed heat, so it tended to resist breaking into small pieces. That suggests the first stars may have been unusually massive compared with many stars today. Massive stars live fast and die young, and their endings can be violent enough to shape their surroundings. They also changed the universe's chemistry by forging new elements which later generations of stars could inherit. So the first stars may have been brief, brilliant bridges between a simple universe and a complex one. Even though we have not seen a true first-generation star directly, astronomers search for their signatures in extremely metal-poor stars that still exist today. Those survivors can act like living fossils, preserving clues about the era when starlight first began. The first galaxies were small, then merged into larger systems. Galaxies did not begin as majestic spirals and giant ellipses. They started as smaller gatherings of gas, stars, and dark matter that formed in the early cosmic web. Gravity then did what gravity does best.
It pulled these early systems together. Mergers were common, and they were creative in a rough way. Collisions could trigger bursts of star formation, stir gas into new shapes, and feed growing central black holes. Over time, repeated merging built larger, more structured galaxies. This is one reason deep images of the early universe often show irregular, clumpy shapes. They are snapshots from a restless era when the ingredients of galaxies were still assembling. Our own Milky Way carries the evidence of this history in its halo of stars and streams. Some of those stars likely came from smaller galaxies that were pulled in and absorbed. A galaxy can be a family tree written in starlight.
Large-scale structure resembles a web because gravity amplifies small differences.
On the biggest scales, the universe looks like a network. There are filaments where galaxies crowd together, nodes where clusters gather, and enormous voids where almost nothing lives. This web is not designed, it is grown. It begins with tiny irregularities. Then gravity magnifies them over billions of years. Where matter is slightly denser, it attracts more. Where matter is slightly thinner, it gets left behind. Over time, this creates long tendrils and vast empty regions that can span hundreds of millions of light years. What is especially fascinating is that this structure can be simulated. Start with a simple early seed pattern, add known physics, and let time and gravity run. The result is a universe that looks uncannily like the one we map with telescopes. When you look at a galaxy survey, you are not just seeing objects scattered randomly.
You are seeing a fossilized flow of matter shaped by gravity across deep time.
Most of the universe is empty, yet its emptiness carries energy. It sounds like a contradiction. Empty space feels like nothing. Yet the universe's expansion seems to be influenced by something that behaves like energy tied to space itself. This idea shows up when we compare how the expansion rate changed over time, and it leads to a startling conclusion. The cosmos is not only expanding, the expansion is accelerating. The simplest way to describe this is with a constant energy density of empty space, often linked to the cosmological constant. If that description is correct, then adding more space adds more of this energy, not less. That makes the future feel strange. As the universe grows, the emptiness becomes an active player in its evolution.
This is one of the deepest puzzles in modern physics, because quantum theories predict vacuum energy in a way that is difficult to reconcile with what the universe appears to do. In a sense, nothingness is not nothing. It has weight in the story of the cosmos. The early universe expanded so fast that it smoothed itself out. One of the most puzzling features of the cosmos is how uniform it is on the largest scales. Regions of the sky that are very far apart have nearly the same temperature, even though there was not enough time for light to travel between them in the standard early picture. This is the kind of mystery that forces new ideas. A proposed solution is that the universe went through a brief period of extremely rapid expansion very early on. During that phase, a tiny patch could have been in contact and well mixed, then stretched to enormous size. It is like taking a small, smooth section of fabric and pulling it so wide that it becomes the background of everything you can see. This kind of expansion would also help explain why the geometry of space appears so close to flat. The remarkable part is that a short early episode could set conditions we still measure today, long after the event itself ended. Inflation explains why distant regions share nearly the same temperature. If the universe inflated from a small, connected region,
then parts of the sky that look unrelated today could have once been neighbors. That would allow them to come into thermal balance before inflation stretched them apart. After inflation, the universe continued expanding more slowly, and the ancient afterglow was released later, carrying a record of that early uniformity. This explanation is compelling because it turns a mystery into a consequence of a specific early process. It also makes predictions. Inflation should not erase all variation.
It should leave tiny fluctuations with a particular statistical pattern, which later become the seeds of structure. So this idea is not only about smoothness, it is also about the texture that remains. When cosmologists compare those predictions with the detailed maps of the cosmic background, they are not just asking whether inflation sounds nice, they are asking whether the universe behaves like it truly had that early growth spurt. In that sense, inflation is a story about cause and evidence stitched together across unimaginable time. Inflation also predicts a pattern of primordial waves in spacetime. If inflation happened, it should have shaken the universe in a very particular way. The stretching would not only smooth space, it would also generate gravitational waves, which are ripples in spacetime itself. These would be different from the waves made by black holes colliding today. They would be ancient, spread across the whole cosmos, and born from the earliest expansion. Their strength would tell us about the energy scale of inflation, which is a clue to physics far beyond any machine we can build. Think of it like hearing the faint vibration of the universe's first great growth spurt. If we could measure that pattern cleanly, it would turn inflation from a clever explanation into a directly tested event. It would also connect the largest thing we know, the universe, to the smallest rules of quantum fields. Scientists hunt those waves through polarization in the cosmic afterglow. The cosmic background light is not only a glow, it also has a subtle orientation, like light filtered through sunglasses. That orientation is called polarization, and it carries a record of what happened when the light last scattered. Gravitational waves from the early universe should leave a special curling pattern in that polarization, a swirl that is hard for other effects to mimic. The challenge is that the signal is faint and the sky is messy. Dust in our own galaxy can produce polarized light too, and it can masquerade as the very thing we seek. So this hunt demands patience, multiple telescopes, and careful cross-checks across different frequencies. It is a beautiful example of scientific humility. The prize is enormous, but the standards are severe. If the signal is real, it would be a direct whisper from the universe's earliest instance, carried to us in the orientation of ancient light. The Big Bang model is tested by many measurements, not one. What makes this story so persuasive is its teamwork. A single clue can mislead, but a web of clues that agree is harder to dismiss. Expansion shows up in the redshifts of galaxies. Light element abundances match what a hot early phase should produce. The cosmic background carries the thermal signature of an early, dense environment. Large-scale structure shows how tiny early variations grew over time. Each line of evidence has its own instruments, its own sources of error, and its own methods of analysis. Yet they converge on a consistent picture. And that consistency is the real triumph. It is also why cosmology keeps evolving. When one measurement disagrees with another, it is not an inconvenience, it is an opportunity. Tension can mean a hidden systematic error, or it can mean new physics waiting just beyond our current model. Hubble's discovery showed galaxies beyond the Milky Way were real. For a long time, people argued about what spiral nebulae were. Some thought they were small clouds inside our own galaxy.
Then Edwin Hubble measured a special kind of variable star in one of these nebulae and used it to estimate distance. The result was staggering. The object was far beyond the Milky Way, which meant it was a separate galaxy. In one step, the universe expanded from one island of stars to a sea of islands. That shift changed everything about the question of origins.
If there are countless galaxies, then the universe has a deep history worth explaining. It also reframed our place in the cosmos. We were not near the center of a single system. We were in one galaxy among many. That realization set the stage for interpreting redshifts as evidence of an expanding universe, which later became a pillar of modern cosmology. Expansion was first interpreted as galaxies receding from each other. When astronomers noticed that many galaxies had redshifted light, the simplest picture was motion. Redshift felt like the Doppler effect, like a siren changing pitch as it passes. If light is stretched, the source might be moving away. That interpretation made the universe feel dynamic and surprising because it suggested that space is not static. It is changing over time. The deeper explanation became clearer. The redshift is not only about galaxies moving through space, it is also about space stretching while the light travels. Still, the recession picture mattered historically because it helped people accept a universe with a timeline. If distances are increasing, then in the past they were smaller. That simple reversal points toward a hotter, denser beginning. It is a powerful example of how a straightforward observation can pull an entire worldview into motion, then force it to grow more subtle as understanding deepens. Gore Lemaitre suggested an expanding universe before the idea gained wide acceptance. Lemaitre was both a scientist and a priest, and he approached the cosmos with an unusual mix of imagination and mathematical rigor. Drawing from Einstein's equations, he argued that the universe might be expanding. And he linked that concept to observations of galaxy redshifts. He even proposed that the universe could have started from an extremely compact state, a kind of seed that later grew outward. At the time, many favored a static universe, including Einstein himself during certain periods. Lamaitre's work illustrates how scientific progress often requires not just data, but the willingness to take equations seriously when they lead somewhere unfamiliar. His legacy also reminds us that cosmology is built by people, and people can be early or late, doubtful or convinced. Ideas need both boldness and evidence. Later provided the boldness, and later observations helped provide the evidence that made expansion difficult to ignore. The phrase Big Bang began as a mocking nickname. The name sounds dramatic, and that drama is part of why it's stuck. It was coined during a period when cosmologists were arguing about how the universe began, and not everyone liked the idea of a hot origin. The phrase was meant to sound a bit silly, as if the whole concept were too explosive to be serious. But language has its own gravity. A memorable label can outlive the argument that created it. Over time, the name became a convenient handle for a complex model, even though it can mislead people into imagining a bomb going off in empty space. That is the irony. A mocking nickname became a household term, and it helped the public remember an idea that is subtle and mathematical. It also shows how scientific stories spread. Data may settle debates, but words shape how ideas travel through culture. Sometimes a phrase can carry an entire concept into the public imagination, even if the phrase is not perfectly accurate. Penzias and Wilson stumbled onto the cosmic afterglow by accident. They were not trying to confirm a theory of cosmic origins. They were trying to solve a problem in their radio antenna, a persistent hiss they could not eliminate. They checked equipment, they considered interference, they even dealt with literal mess in the apparatus.
Yet the noise remained steady and coming from every direction. That is the key detail. A local source would vary with pointing direction or time, but this signal seemed universal. At the same time, other scientists had predicted that a hot, early universe should leave behind a faint background of radiation. The match between prediction and accident was striking. It is one of science's most charming moments. An engineer's nuisance became a cosmologist's treasure. It also shows how discoveries can arrive sideways. Sometimes you find the universe because you are trying to fix a machine, and the machine refuses to stop listening to the sky. A faint hiss in radio antennas helped confirm a hot, early universe. The discovery of that all-sky radio noise did more than add one more fact. It changed the status of the whole model. Without a relic background, a hot, early phase could be dismissed as speculation. With it, the universe carried a direct thermal fingerprint of its youth. That hiss was not a signal from a star or a galaxy or even a cluster. It was a diffuse glow left from a time when the universe itself was the source. It also helped settle a major debate between different cosmological pictures, because the steady-state idea had no natural reason to produce a sky-filling thermal background with the observed properties. The hiss did not tell the whole story on its own, but it gave the story a physical anchor. It is remarkable that something so cosmic could first appear as an irritation in a receiver, like the universe insisting on being heard. Kobe measured the afterglow spectrum with stunning precision. By the late 20th century, the cosmic background had been detected, but its exact shape still mattered. A hot, early universe predicts a very specific thermal spectrum, not a rough approximation. Trobe, a satellite built to measure that spectrum above the blurring effects of Earth's atmosphere, delivered a remarkably clean result. The afterglow matched a near-perfect blackbody curve, which is exactly what you expect from a universe that was once hot, dense, and in thermal balance. That measurement was not flashy to the eye, but it was devastatingly persuasive to the mind. It is the kind of evidence that feels like a lock clicking shut. Once you have a thermal spectrum that precise, many alternative explanations lose their footing. Kobe also opened the door to finer questions. If the spectrum is that perfect, then the remaining details like tiny anisotropies and polarization become the next frontier for learning how structure began. Kobe also found tiny temperature variations that later missions mapped in detail. Those minute mottlings in the cosmic background were a turning point, because they were the first clear glimpse of the universe's original unevenness. Kobe showed that the early cosmos was not perfectly smooth. It carried faint, warm, and cool patches across the sky. That discovery mattered for a simple reason. Without early irregularities, gravity would have had nothing to build with. Once the variations were known to exist, scientists could treat them like fingerprints from a formative era. Their sizes and strengths revealed how matter and radiation interacted, and they offered clues about what ingredients the universe contained. It also changed what came next. Better missions were designed to map the pattern with far finer detail, the way a blurry photo invites a sharper one. From a tiny signal, an entire precision science was born. Webb refined the universe's age and composition using microwave maps. Webb did not just take a prettier picture of the cosmic background, it measured the pattern so well that the ripples became a tool for taking the universe's inventory. Peaks and dips in the map trace how early matter moved, how pressure pushed, and how gravity pulled. By comparing the observed pattern with predictions, scientists could estimate how much ordinary matter exists, how much invisible matter is needed, and how dominant the mysterious accelerating component must grow. B. It also tightened the estimate of the universe's age by tying cosmic history to measurable features in the sky. This was a shift from broad storytelling to precision bookkeeping. It also gave a shared reference point. Different fields could anchor their work to the same cosmic parameters, and arguments about numbers became sharper and more testable. A map of think microwaves became a ruler for the whole universe's timeline. Planck pushed those measurements to even finer resolution. Planck took the cosmic background and measured it with extraordinary sensitivity across multiple frequencies. That matters because the sky contains distractions. Dust and energetic particles in our own galaxy can add foreground signals that must be separated from the true cosmic pattern. By observing in many bands, Planck could disentangle more of that clutter and reveal the background with greater clarity. It sharpened the small-scale features, and those features are where subtle physics hides. Tiny differences in the pattern can tell you about how quickly the early universe expanded, how matter clumped, and how light scattered through the primordial plasma. Planck also strengthened the sense that cosmology is a high-precision field, with numbers that can be compared to multiple decimals. That success came with a twist. As measurements became more precise, certain disagreements with other methods became harder to ignore. Better clarity can also reveal deeper puzzles. Big Bang nucleosynthesis predicts helium abundance seen in old gas clouds long before stars could manufacture helium. The early universe created a large share of it during its first hot minutes. The theory makes a specific prediction. Given the density of ordinary matter, you should end up with a particular fraction of helium compared with hydrogen. Astronomers can test this by studying very old, very pristine regions of gas. These environments have seen little stellar processing, so they preserve an early chemical record. When the measured helium fraction matches the prediction, it is like finding a timestamp from the universe's infancy that still reads correctly. The beauty here is that the physics is simple and strict. Nuclear reactions in a rapidly cooling cosmos leave limited room for improvisation. This is why helium abundance is not just a curiosity. It is a consistency check that links atomic nuclei to the largest story imaginable. And it does so with real numbers from the sky. Deuterium measurements act like a cosmic baryon counter for normal matter. Deuterium is fragile. It is easily destroyed inside stars, and it is not made in large amounts by ordinary stellar processes. That makes its cosmic abundance especially valuable, because it mostly reflects what happened in the early universe, rather than later recycling. The theory of early element formation predicts how much deuterium should survive, and the answer depends strongly on how many baryons, meaning protons and neutrons, existed per photon back then. Measure deuterium in ancient, relatively unprocessed gas, and you can infer the amount of normal matter in the whole universe. It is like weighing the cosmos using a rare isotope as a scale. This is also why deuterium is treated with such care. Astronomers look for clean targets, and they cross-check results because a small observational bias could mislead a big conclusion. When the measurements agree, they pin down the baryon budget with remarkable confidence. Galaxy surveys map ancient ripples as a ruler for cosmic distances. When we map millions of galaxies, we are not only collecting dots.
We are measuring the faint preference for a particular separation scale that was set by early pressure waves. That scale acts as a standard ruler embedded in the distribution of matter. If you know its true size from early universe physics, then you can compare it with how large it appears at different distances. That comparison reveals how the universe expanded across time. What makes this so powerful is that it does not rely on a single type of object. It uses statistics across vast volumes of space. It also links two eras. A feature born in the primordial plasma becomes a measuring tool for the later universe filled with galaxies. The surveys themselves are feats of patience and engineering. They record spectra, infer distances, and build three-dimensional maps. From those maps, cosmologists extract an expansion history written into the cosmic web itself. Supernova observations revealed expansion is accelerating, not slowing.
White dwarf explosions called Type 1 supernova can be used as distance indicators because their brightness follows a calibratable pattern. When teams measured these explosions in very distant galaxies, they found something startling. The supernova looked dimmer than expected in a universe that was slowing down. The simplest interpretation was that the universe had been expanding more slowly in the past than it is now. That means expansion has been speeding up. This was not a subtle philosophical shift. It changed the expected fate of the cosmos and introduced a new, dominant component to the energy budget. It also showed how the universe can surprise us using ordinary light. A star's death in a remote galaxy became evidence about the behavior of space itself. The discovery also demanded caution. Astronomers had to rule out dust, evolution, and selection effects. The result survived that scrutiny and became one of modern cosmology's defining moments. Cosmic parameters can be inferred by fitting many datasets at once. Modern cosmology works like a courtroom with multiple witnesses. The cosmic background gives one kind of testimony. Galaxy clustering gives another. Supernova distances provide another. Gravitational lensing adds yet another. Each dataset has different sensitivities and different weaknesses, so combining them can break degeneracies that would confuse any single approach. When the fits converge, you obtain a set of parameters that describe the universe with surprising economy. Those numbers include the expansion rate, the matter fractions, and the amplitude of early fluctuations. The method is powerful, but it also demands discipline. You must account for uncertainties, biases, and correlations. You must check that improvements in one measurement do not hide errors in another. When done well, the result is a coherent cosmic model that can predict new observations. This is why cosmology feels both grand and meticulous. It aims to describe everything, and it does so by carefully weighing many imperfect glimpses of the sky. There is a tension between two precise ways of measuring expansion today. One method measures the expansion rate by looking at the early universe and evolving a model forward. This uses the cosmic background and related physics as a starting point. Another method measures it locally by building a distance ladder. That ladder can involve pulsating stars, calibrated supernova, and distances to nearby galaxies. Both approaches have become impressively precise, and that is the problem. They do not agree as well as they should. The gap is not enormous, but it is stubborn. It has survived years of improved data and careful reanalysis. This tension matters because it suggests that either hidden systematics remain or the standard model of cosmology is missing an ingredient. It turns a number into a mystery. It also makes the present era exciting. Precision is no longer only about tightening error bars. It is about deciding whether the universe is quietly telling us that our current story is incomplete. That disagreement may hint at new physics beyond standard cosmology. If the expansion tension is not a measurement issue, then something in the cosmic recipe may need revision. Possibilities include an early burst of extra energy that briefly changed the expansion rate, or a subtle new particle that altered conditions before the cosmic background was released. Other ideas involve neutrino properties, interactions in the dark sector, or changes in how gravity behaves on large scales. Each proposal must do a hard thing. It must resolve the tension without ruining the many successes of the standard model. That is a high bar, and it keeps speculation honest. This is also how science advances. A small inconsistency can become a doorway to a larger understanding, but only if it survives intense testing. For now, the disagreement acts like a persistent note in an otherwise harmonious chord. It may fade with better calibration, or it may grow into a new movement in physics. Either outcome teaches us something real. The universe likely had no preferred center. Expansion happens everywhere. If you run the cosmic movie backward, everything gets closer together, but it does not point to a special spot you could mark on a map. Expansion is built into the geometry, so every galaxy can look out and see other galaxies receding in all directions. It is like raisins in rising dough. No raisin is the middle of the loaf, yet every raisin sees the others drifting away as the dough swells. This idea can feel slippery because our brains love a central stage. The universe refuses to provide one. The Big Bang is not a firework launched from a single location. It is an early state that happened everywhere at once, in the sense that space itself was denser and hotter everywhere. That is why asking, "Where did it happen?" is often the wrong question. The better question is, how did it change? Expansion does not mean galaxies fly through space like shrapnel. It is tempting to imagine galaxies blasting outward into emptiness, but that picture leads to confusion. The key point is that the space between distant galaxies is stretching, and that stretching changes the distance, even if the galaxies are not pushing themselves away. This is why cosmologists say the universe expands rather than explodes. It also helps explain a famous curiosity. Very distant galaxies can have a recession speed that seems faster than light, and relativity is still safe. Nothing is locally outracing a beam of light through space. Instead, the route between us and the galaxy is lengthening. You can picture it like an ant walking on a rubber band that has been pulled apart. The ant can obey every speed limit and still fail to reach the far end if the band stretches quickly enough. Expansion is motion of distance itself. On small scales, gravity can beat expansion and bind galaxies together. Cosmic expansion is a large-scale effect, and it does not act like a wind that tries to pry everything apart. Where matter is tightly bound, gravity and other forces hold the structure together and ignore the slow stretching of the universe. That is why atoms do not expand, your body does not expand, and solar systems do not drift apart because of the Big Bang. Even groups of galaxies can remain bound if their mutual gravity is strong enough. This creates a universe with two simultaneous truths. On the grandest scales, distances grow and the cosmic web stretches. Locally, islands of matter can stay intact, orbit, collide, and merge. It is a beautiful balance. Expansion sets the stage, but gravity writes the local drama. Understanding which effect dominates depends on scale, mass, and time. And this is why cosmology requires both geometry and dynamics. The Milky Way and Andromeda are moving toward each other even as the universe expands. If expansion were the whole story, every large galaxy would be receding from every other forever. Andromeda challenges that simple picture. It is near enough and massive enough for local gravity to take over. The two galaxies share the same neighborhood, along with smaller companions, and their mutual attraction is pulling them together. Over time, their halos interact and their trajectories bend inward instead of outward. This does not contradict cosmic expansion. It highlights that the universe is not governed by a single, uniform motion. It is a woven structure of bound regions set within an expanding background. When the Milky Way and Andromeda finally encounter each other, the event will unfold slowly on human timescales, reshaping both galaxies through tides, bursts of star formation, and long streams of stars flung into new paths. It is a future shaped by gravity, occurring inside a universe that continues to expand around it. The early universe produced no heavy elements beyond lithium in quantity. In the beginning, the periodic table was almost empty. The first minutes could make hydrogen and helium efficiently, and it could leave behind only a small trace of lithium. Then, the universe cooled too quickly for heavier nuclei to be built in that global way. This early simplicity had consequences. Without abundant heavier elements, there were few efficient ways for gas to radiate heat away. And heat matters because cooling helps clouds collapse. The first structures had to form under these constraints, using a limited chemical toolkit. It also means that every heavy element you have ever seen, from the calcium in bone to the silicon in sand, is a later invention of the cosmos. The early universe set the initial conditions, but it did not supply the ingredients for rocks, oceans, or biology. Those came later, after generations of stars learned how to manufacture complexity and return it to space. Stars later forged carbon, oxygen, and iron through nuclear fusion. Once stars formed, the universe gained longevity factories that could keep nuclei hot and dense for millions to billions of years. Inside stellar cores, hydrogen fusion provides the first major energy source. As massive stars evolve, they build helium into carbon, then carbon into oxygen and neon, and onward through stages that can create elements like magnesium and silicon. Iron is a special turning point. Fusing iron does not release energy the way lighter fusion does, so it marks a limit for what ordinary fusion can accomplish in a star's core. That limit shapes stellar endings. It also shapes life, because carbon chemistry underpins biology. Oxygen drives metabolism, and iron becomes a common component of planetary interiors and many living systems. When you think about the Big Bang, it is worth remembering that it delivered the simple beginning, and stars delivered the rich middle, turning a mostly hydrogen universe into a place with diverse materials and possibilities. Supernova and neutron star mergers created many elements heavier than iron. To build elements heavier than iron in large quantities, the universe needs environments more extreme than a steady stellar core. Two of the leading sites are dramatic. One is the death of a massive star in a supernova, where shock waves and intense conditions can drive rapid nuclear reactions. Another is the collision of neutron stars, where matter packed to near nuclear density is flung outward and flooded with neutrons. In such places, nuclei can capture neutrons quickly and then transform into heavier elements as they settle into stability. This is how many rare heavy elements are thought to form.
including some found in jewelry and electronics. Astronomers look for these fingerprints in the light from explosive events and in the chemical patterns locked into ancient stars. Each detection is like finding a shipping label from a cosmic foundry. The heavy elements in the world around you are not generic. They are souvenirs of violence stitched into matter. The first black holes may have grown rapidly from early massive stars. In the early universe, conditions may have favored very massive stars, and massive stars live fast. Many end by collapsing into black holes. If those first black holes formed early enough, and if they found abundant surrounding gas, they could grow quickly by feeding. This matters because we observe quasars very far away, which means we see them very early in cosmic time, and some host black holes that are astonishingly massive. That raises a puzzle. How did they grow so big so soon? One pathway is rapid accretion, where gas spirals in and releases enormous energy. Another possibility is frequent mergers of smaller black holes in dense early environments. These ideas turn black holes into characters in an origin story. They are not only endpoints of stars, they may be architects of early galaxies, influencing star formation by heating and stirring gas with powerful radiation and jets. The earliest black holes could have helped shape the cosmic neighborhood they lived in. Some models allow primordial black holes formed before the first stars. There is another, more speculative route to black holes, and it begins even earlier than starlight. If the infant universe contained regions that were slightly denser than average, gravity could in principle crush some of those regions into black holes directly, without any star as an intermediate step. The masses could vary widely depending on when they formed. Some would evaporate quickly through quantum effects, while others could survive to the present. This idea is compelling because it connects early universe physics to a present-day mystery. It suggests black holes might carry information from conditions we cannot recreate and from times we cannot observe with ordinary light. It is also an idea that invites testing. Primordial black holes would leave signatures through gravitational lensing, through their influence on structure, or through subtle effects on cosmic backgrounds. The models are a reminder that cosmology still has room for surprises, especially when it comes to what formed first. If primordial black holes exist, they could contribute to dark matter. Dark matter is known by its gravity, and black holes are gravity in a concentrated form. So it is natural to ask if some fraction of the missing mass could be black holes made in the early universe. The challenge is that the idea must survive many constraints. If too many primordial black holes had certain masses, we would expect more lensing events of background stars, or we might see effects on the cosmic background. Or we might notice disruptions in stellar systems. Observations have ruled out large ranges of possibilities, but not all of them. That leaves pockets of parameter space where primordial black holes could still play a role. Even a partial contribution would be exciting, because it would tie dark matter to an object we already understand in general relativity. It would also make dark matter less like an invisible particle and more like a population of hidden compact objects. Either way, the search sharpens our picture of what the universe is made of. Cosmic background anisotropies reveal the universe is very close to flat. The modeled pattern in the cosmic background is more than a pretty map. It is a geometry test. In curved space, light and distances behave differently, and that changes how large early patterns appear on the sky.
When scientists measure the characteristic sizes in the background, they find they line up with what you would expect if space is extremely close to flat overall. That does not mean the universe is simple. It means the large-scale geometry does not noticeably curve like a sphere or saddle within our measurement precision. This is astonishing because slight curvature could have grown important over cosmic time. Instead, the universe seems finely balanced. This result also links to early expansion ideas, because a rapid early stretching would naturally push space toward flatness, like pulling wrinkles out of fabric. A subtle sky pattern becomes a statement about the shape of reality.
Flat means geometry.
Not that the universe is small or shallow. When people hear flat, they picture a pancake universe with edges you could fall off. In cosmology, the word is about geometry. It describes how parallel lines behave, how triangles add up, and how like paths compare with the rules you learned in school. A flat universe follows the familiar geometry of Euclid on large scales. Triangles add up to about 180 degrees, and light does not curve because of global geometry alone. That has nothing to do with whether the universe has an end or whether it is wide in some direction and narrow in another. Flat is also not the same as empty. A flat universe can still be packed with matter, radiation, and mysterious components, and all of them can influence how expansion evolves. It is a reminder that everyday words can mislead in science. Sometimes the most important meaning is the one you cannot picture easily, but you can measure.
Flat space can still be infinite, depending on global topology.
Geometry tells you about local rules, but topology tells you about the overall layout. A flat surface can be infinite, like an endless plane, but it can also be finite if space connects back on itself in the right way. A classic analogy is a video game world, where walking far enough in one direction brings you back to where you started. Locally, it can feel flat, yet globally it loops. Some cosmological models allow a universe like that in 3 dimensions, where space is flat in its geometry, but still wraps around. If that were true, they could be repeating patterns in the sky, like the same distant region appearing in multiple directions at different times. Searching for such patterns is difficult, and nothing conclusive has been found. But the idea is thrilling. It shows how the universe could be both bounded and edgeless, with flatness and finiteness coexisting.
We have not measured whether the universe wraps around itself.
It is possible that space has a kind of cosmic shortcut where traveling far enough in one direction eventually brings you home from another. If that were the case, the sky might contain subtle clues like matching circles or repeating arrangements in the background glow. Created because light took different routes through a looping space. The challenge is that the universe is vast, and we only observe a finite region. If the wraparound scale is larger than what we can see, then the evidence would be out of reach. Even if the scale is smaller, the signal could be masked by noise, foreground interference, and the complexity of how light was scattered in the early universe. So this becomes a fascinating kind of absence. We can test certain possibilities, rule some out, and leave others open. It is a reminder that cosmology does not only ask what happened.
It also asks, what kind of space are we living in?
The answer might be stranger than distance alone suggests. The cosmic neutrino background should exist, though it is extremely hard to detect. Neutrinos are almost ghost-like. Trillions pass through you every second, and you do not feel a thing. In the early universe, neutrinos were produced in huge numbers, and as space expanded, they cooled into a relic background, similar in spirit to the cosmic microwave background, but even more elusive. The difference is interaction. Photons scatter easily, so we can catch them with antennas and detectors. Neutrinos barely interact at all. So a true primordial neutrino background is extraordinarily difficult to observe directly. Yet its existence is not just a wish, it is a robust prediction of early universe physics. Even if we cannot bottle these relic neutrinos, their effects can still be inferred.
They influence how quickly the universe expanded during key eras, and they slightly alter the growth of structure. In that way, an unseen ocean can still leave tidal marks. Detecting it would be like hearing a deeper layer of the universe's earliest chorus. The earliest moments are described by particle physics under extreme conditions. At the beginning, the universe was not a collection of galaxies. It was a laboratory where energy, fields, and particles constantly transformed into one another. The rules that matter most there are the rules of particle physics, because temperatures were so high that ordinary matter could not exist in familiar forms. The ingredients list of reality may have been different, with particles appearing and disappearing as conditions changed. This is why cosmology and particle physics are intertwined. When cosmologists ask what happened very early, they often end up asking what particles existed, how they interacted, and what symmetries held. When particle physicists test high-energy theories, they often ask what those theories would have done to the infant universe. It is a partnership across scales. The largest object we can study becomes evidence about the smallest laws, and the smallest laws become a story about the whole sky. The Big Bang model does not yet explain why constants have their values. The model describes how the universe evolves given certain rules, but it does not fully explain why the rules are set the way they are. Why does gravity have its particular strength? Why do particle masses take the values they do? Why does the vacuum behave as it does? These numbers shape everything. Small changes could prevent stable atoms, alter stellar lifetimes, or erase the chemistry that makes complex structures possible. Scientists explore many ideas here. Some search for deeper, unifying theories that would make the constants inevitable. Others consider whether our observed values could be selected from a wider landscape of possibilities. This question is fascinating because it sits at the edge of what science can currently test. It is not a weakness of cosmology, it is a frontier. The Big Bang story tells us how the universe grew up. The constant question asks why this universe had this particular personality in the first place. It also does not explain why there is more matter than antimatter. The laws of physics often treat matter and antimatter as mirror partners. In the early universe, they were created together in abundance, and they could annihilate back into radiation. If the balance had been perfect, you would not have stars, planets, or air. You would have mostly light. Yet the universe clearly ended up with a leftover supply of matter. That leftover is everything solid you have ever touched. The mystery is not whether it happened. The mystery is how the process must have occurred under conditions that allowed tiny asymmetries to become permanent. And it must involve physical effects that slightly favor matter over antimatter. This is one of the most thrilling open problems because it ties existence itself to subtle microscopic behavior. It also shows how cosmic history depends on tiny differences. A small imbalance early on becomes a universe with structure later. Solving this would connect the first moments to the fact that anything remains at all. Baryogenesis is the name for processes that could create that imbalance. This is the umbrella term for the universe's method, whatever it was, for tipping the scales toward matter. Any successful mechanism must meet strict requirements. It must allow matter number to change, it must treat matter and antimatter differently, and it must occur out of equilibrium, so the universe cannot simply reverse it.
Those conditions are demanding, and they make baryogenesis a powerful filter for theories beyond the standard model of particle physics. Different ideas place the action at different times, some connected to very early phase changes, others to neutrino physics, and others to physics at energies far higher than we can reach in accelerators. What makes this so compelling is the investigative nature of the hunt. The crime scene is the entire cosmos, and the clues include tiny symmetry violations measured in laboratories, along with the basic fact that galaxies are here at all. Each improvement in measurement tightens the list of suspects. The aim is not a clever narrative. It is a mechanism that obeys nature's rules and matches the universe we see. Early phase transitions may have altered the universe's forces. As the cosmos cooled, it likely crossed threshold moments where the behavior of fields shifted and new distinctions appeared.
In everyday experience, water freezing is a familiar example of a phase transition. In the early universe, such transitions could have involved the forces themselves, changing how particles interact and how properties like mass emerge. These events may have released latent energy, created exotic defects, or generated new populations of particles. They might also have affected baryogenesis if conditions allowed matter to gain a slight edge. The idea is dramatic because it suggests the universe was not only cooling, it was reorganizing its fundamental rules as it cooled. This is also why cosmologists care about symmetry. Symmetry can be present at high energy, then break as the universe expands, leaving behind new physics in a lower energy world. If we could map these transitions more clearly, we would be reading a timeline of the universe, learning what kind of universe it would become. The electro-eq era shaped how particles gained mass through symmetry breaking. Very early on, the universe was so hot that forces we now treat as separate behaved as one combined electro-eq force. As expansion cooled everything, a field that filled space settled into a new state, and that shift changed how certain particles moved through it. Some particles began to experience resistance that shows up to us as mass. Photons stayed massless, which is why light can travel freely across the cosmos. Other particles gained mass, which helped shape what could exist later, from stable atoms to longeved stars. This is one of the strangest ideas in physics, because it means mass is not only a property of an object, it is also a relationship between an object and the state of space itself. The early universe did not just make matter, it also set the rules that matter must live by. Quark-gluon plasma once filled the cosmos before protons could form. Before there were protons, the universe was too hot for quarks to stay confined inside them. Quarks and gluons moved in a dense energetic mixture, where the usual boundaries of particles were not yet locked into place. Then cooling pushed the universe through a transformation. Quarks became bound into head, including protons and neutrons, and the cosmos gained the familiar building blocks of later chemistry. This transition is sometimes compared to steam condensing into liquid, not because it is the same process, but because the whole character of the material changed as temperature fell. It is a wild thought that every proton in your body traces back to a time when protons could not exist. The universe had to pass a thermal threshold before it could even form the particles that would later form atoms.
Our solid world depends on that ancient shift from free quarks to confined matter. Particle colliders recreate tiny echoes of early universe conditions. On Earth, we cannot rewind the cosmos, but we can imitate a few of its early ingredients for a fraction of a second.
In heavy ion collisions, nuclei are smashed together at enormous energies, and the impact can briefly produce a state of matter closer to the early universe than to everyday solids and gases. Detectors then watch what sprays out, and those particle patterns act like clues to what the hot phase was like. Researchers look for signs of collective flow, energy loss, and other behaviors that suggest matter is acting as a strongly interacting fluid rather than a simple gas of particles. It is remarkable that a machine built on a planet can probe conditions that once filled the entire universe. Colliders turn cosmology into an experimental science in miniature. They cannot reproduce the whole early universe, but they can test pieces of its physics, and pieces can still change the story. The cosmic background is not light from the first stars. This common mix-up is understandable because both involve very old light. The cosmic background comes from a time before any stars existed. It was released when the universe was still a hot, nearly uniform sea of matter and radiation. Long before galaxies had assembled, starlight, by contrast, is produced inside stars and carries fingerprints of stellar atmospheres like sharp spectral lines and distinctive colors. The cosmic background is different. It is an all-sky glow with a near-perfect thermal spectrum, and it does not point back to individual sources. It points back to a time when the universe itself was the source. Keeping this distinction clear matters because it changes what the signal can tell us. Starlight teaches us about astrophysics and chemical history. The background teaches us about the early conditions that set the stage for everything that came later. It is older. It comes from when the universe first cleared. There was a moment when the universe stopped acting like a fog and started acting like transparent space. Before then, light could not travel far without being scattered, so the cosmos was bright, but visually trapped. When conditions changed, photons finally streamed freely, and they have been traveling ever since. What we observe today is sometimes called the surface of last scattering. Not because it is a physical wall, but because it marks the last time those photons were repeatedly bounced around. It is also a strange kind of time machine. No matter where you look, you are seeing a shell of that same era at different points in space. Even nearby directions in the sky correspond to regions that were far apart back then, which is why the subtle pattern across the shell is so informative. The universe cleared once, and it left behind a sky filled with evidence. The afterglow has been stretched from visible light into microwaves. As the universe expands, it stretches wavelengths in transit, like a tune lowered as the instrument grows. The cosmic background began much hotter than it is now, and hotter radiation peaks at shorter wavelengths. Over billions of years, expansion lengthened those wavelengths until they moved into the microwave band. This stretching also cools the radiation in a predictable way, because longer wavelength light carries less energy per photon. That is why the background temperature today is only a few degrees above absolute zero. It is not because the universe cooled, like a room losing heat into outside space. It cooled because space itself expanded, and that expansion diluted energy and stretched light.
The result is a signal that is both ancient and current, arriving right now as microwaves from every direction. With the right instruments, we can measure that ancient heat long after it faded from visible brightness. As space expands, it also stretches wavelengths, creating cosmic redshift. Redshift is the universe's built-in stamp on traveling light. When a galaxy emits light, that light begins its journey with a certain wavelength. While it travels, the scale of space can increase, and the wave is stretched along with it. By the time it arrives, its wavelength is longer, and its color has shifted toward the red end of the spectrum. This is not only an effect of motion through space, it is an effect of the changing geometry of space during the journey. That is why redshift is so central to cosmology. It links what we measure in a spectrum to the history of expansion between then and now. It also gives every photon a story. The light left a different universe than the one it arrived in, and the stretching of its wavelength is the trace of that change. In a sense, the universe signs its name on every distant being. Redshift is how we tell distant galaxies are seen in the past. When astronomers spread a galaxy's light into a spectrum, they look for recognizable features like patterns from hydrogen or other common elements. Those features appear shifted compared with laboratory measurements. The amount of shift gives the galaxy's redshift. And redshift can be translated into how long the light has been traveling, once you adopt a cosmological model that gives a look-back time. It is one of the few ways we can place distant objects on a timeline without knowing their full histories. With redshift, a deep survey becomes a kind of layered museum. Nearby galaxies represent later chapters, while high redshift galaxies reveal earlier stages of growth and change. This is also why the same telescope can study both structure and history at once. By measuring redshifts, we do not only map where galaxies are, we map when we are seeing them. Distance becomes time, and the sky becomes an archive. The first molecules formed before the first stars, including simple hydrogen molecules. Even in a universe with almost no heavy elements, chemistry found a way to begin. As the cosmos cooled and neutral atoms became common, small numbers of molecules could form, especially molecular hydrogen. The process was inefficient, but it did not need to be fast to matter. A tiny fraction of molecules can have an outsized effect because molecules can radiate energy through rotational and vibrational transitions. There were also more exotic early molecules like helium halide, which may have been among the first molecular bonds in the cosmos. These early molecular steps are fascinating because they happened in darkness, before starlight and before planets. They show that complexity does not begin with biology. It begins with the universe becoming cool and stable enough for atoms to stick, then for molecules to form, and then for new pathways to open. Chemistry did not wait for stars to turn on. It started assembling in the shadows. Cooling by those molecules helped the earliest stars collapse and ignite. Gravity can pull gas inward, but without a way to lose heat, a collapsing cloud builds pressure and can stall. Early molecules, especially molecular hydrogen, gave primordial gas a way to radiate energy away. That cooling allowed clouds to contract further, reach higher densities, and eventually trigger star formation. The first star-forming regions were likely small halos of dark matter filled with simple gas, and molecular cooling helped that gas settle into dense cores. This does not mean molecules did all the work. Gravity provided the pull, and the expanding universe set the timing. Molecules provided the escape hatch for energy. The result was the first ignition of starlight. which then began transforming the universe in new ways. This is one of the most satisfying chains in cosmic history. Expansion cools the universe. Cooling allows molecules. Molecules allow collapse. Collapse allows stars. And stars begin the long story of heavy elements, planets, and the conditions that make complex worlds possible. Reionization is when early starlight stripped electrons from atoms again. After the universe first became neutral, it did not stay that way forever. Gravity kept gathering gas, and the first luminous sources switched on in pockets of the cosmic web. Their energetic ultraviolet light began tearing electrons away from hydrogen once more. This did not happen everywhere at once. It spread like overlapping bubbles growing around young galaxies and star-forming regions. In some places, neutral gas lingered longer, and in other places, it vanished early. That patchiness matters because it affects how later light travels through space, and it changes how easily gas can cool and collapse. Astronomers chase this era using clever signals, including the way neutral hydrogen would glow or absorb at a radio wavelength called 21 centimeters.
When we map reionization in detail, we will be watching the universe wake up again. Not with a single sunrise, but with many. Quasars helped reionize the universe by pouring out intense radiation. Quasars are powered by supermassive black holes, feeding on infilling gas. As material spirals inward, it heats to extreme temperatures and shines across the spectrum, including strong ultraviolet and X-ray light. That makes quasars natural ionizers because their photons carry enough punch to strip electrons from atoms far away. In the early universe, even a small number of bright quasars could have carved large ionized regions in surrounding gas. They also give us a way to test the state of the cosmos. When we look at very distant quasars, we sometimes see a deep absorption feature from intervening hydrogen. It is called the Gunn-Peterson trough, and it signals that neutral gas was still common along the line of sight. So quasars play two roles at once. They may have helped change the universe, and they also act as backlights that reveal how much of that change had already happened. Cosmic background polarization preserves information about early scattering events. The cosmic background is not only a map of temperature. It also carries a faint pattern in the orientation of its electric field, created when light scattered from electrons under slightly uneven conditions. That polarization is valuable because it separates different strands of cosmic history. One pattern, known as E-modes, arises naturally from density variations in the early plasma and has been measured with striking precision. Another pattern, called B-modes, is more difficult to produce and can be generated by gravitational lensing or by primordial gravitational waves, if such waves exist. There is also a feature connected to reionization. When the first galaxies reionized the universe, newly freed electrons scattered the background light once again, adding a large-scale polarization signal. In this way, polarization acts like a second script layered over temperature. It helps resolve degeneracies, test ideas about inflation, and reveal how the universe evolved long after the first clear light was released. Gravitational lensing distorts the background, revealing hidden mass along the way. As ancient light travels to us, it passes through a universe filled with matter, both visible and invisible. Gravity bends space-time, and that bending deflects the paths of photons. The result is subtle warping of the background pattern.
hot and cold spots get slightly shifted and sharp features become gently smeared. This is not a nuisance, it is a measurement. By studying the statistical distortions, scientists can reconstruct a map of the total mass that did the bending, integrated across huge distances. What makes this so exciting is that lensing responds to gravity, not to brightness. It does not care whether the mass is shining, dusty, or completely dark. It only cares that the mass is there. So the cosmic background becomes a backlit screen, and the entire universe between us and that screen becomes the lens with enough precision. Lensing even lets us test how structure grew over time, and whether gravity behaves exactly as expected on the largest scales. That lensing map is one of our best traces of dark matter. A lensing reconstruction is like an X-ray of the cosmic web. It highlights where mass is concentrated, even when ordinary matter is faint or missing. When researchers compare lensing maps with galaxy surveys, they can see how luminous matter sits inside larger, dark matter structures, and they can quantify the bias between light and mass. Lensing also helps constrain key numbers that describe clustering in the universe, including how strong the typical density variations are on certain scales. It can even put pressure on the masses of neutrinos, because heavier neutrinos subtly suppress small-scale structure and leave fingerprints in the lensing signal. Another strength is its cleanliness. Lensing does not rely on the complex astrophysics of star formation, and it avoids assumptions about how bright objects ought to be. It follows gravity directly. That is why it has become central to modern cosmology. When you want to map the invisible, you look for how it bends what is visible. The universe's expansion history affects how structures grow over time. Gravity is always trying to pull matter together, but expansion acts like a moving floor that can make collapse harder. If the universe expands faster at a given era, matter has less time to clump before distances stretch further. If expansion is slower, gravity has more opportunity to amplify small differences into large structures. Cosmologists describe this with a growth factor, which tracks how density variations strengthen as the universe ages. They can measure growth in several ways, including how galaxies cluster, how their motions create redshift space distortions, and how lensing signals evolve with distance. This is why expansion is not only about where galaxies are, it is also about what galaxies can become. Two universes with the same ingredients but different expansion histories would grow different cosmic webs. When we combine measurements of expansion with measurements of growth, we get a powerful consistency test. If the two stars disagree, it could signal new physics or a missing ingredient in the cosmic recipe. Dark energy suppresses growth by pulling space apart faster. When dark energy dominates, expansion accelerates, and that changes the future of structure. Matter can still collapse in already bound regions, but new growth on very large scales slows down because the universe is stretching too quickly for gravity to gather fresh material efficiently. You can think of it as the cosmic web losing its ability to tighten its threads. This suppression is not just philosophical. It leaves measurable traces. It changes how clustering evolves with time, and it can create a subtle effect on the cosmic background, called the integrated sex-wolf effect, where photons gain or lose energy as gravitational potentials evolve. Dark energy also affects how we interpret surveys, because the same set of early seeds can lead to different present-day structures, depending on how acceleration turned on. So dark energy is not only a driver of expansion, it is a shaper
of what never forms. It influences the amount of large-scale structure the universe is allowed to build. Some theories replace dark energy with modified gravity on cosmic scales. Instead of adding a new energy component, some ideas tweak how gravity works over very large distances. In these models, acceleration emerges because gravity behaves differently than general relativity predicts when space is vast and densities are low. The challenge is that any modification must hide in places where Einstein's theory has been tested. These support extremely well, like the solar system, while still changing cosmic behavior. Many proposals use screening mechanisms that make deviations small in dense environments and larger in the emptier cosmic background. These theories can be tested by comparing different ways of weighing the universe. Galaxy motions respond to the gravitational force, while lensing responds to space-time curvature. And in modified gravity, those two can separate. Researchers look for mismatches between dynamical mass and lensing mass, and for changes in the growth rate of structure.
It is a thrilling possibility because it would mean the universe is not driven by a mysterious energy at all. It would mean our map of gravity itself needs a cosmic scale correction. Cosmology relies on assuming large-scale uniformity, and it is repeatedly tested. The cosmological principle says that on the largest scales, the universe is roughly the same everywhere, with no special direction and no special location. This assumption is not a leap of faith, it is checked. The cosmic background is extraordinarily uniform after removing local motion effects. Galaxy surveys show that while matter is clumpy on smaller scales, the distribution approaches homogeneity when you average over truly huge volumes. Researchers also test isotropy by comparing expansion measurements in different directions, and by checking whether the statistical properties of cosmic maps depend on where you look.
These tests matter because the principle underpins how we translate redshift into distance and how we infer the universe's overall parameters. If the universe was strongly anotropic or inhomogeneous on the largest scales, many conclusions would have to be revisited. So cosmology treats uniformity as a working hypothesis with receipts. The universe seems to cooperate, but scientists keep checking because the stakes are high. Even tiny departures from uniformity can be measured across the sky. Once you have precise maps, you can start asking whether the universe is perfectly statistically uniform or only very close. Scientists search for hemispherical asymmetries, preferred directions, and subtle deviations from a purely random Gaussian pattern in the early fluctuations. They also look for traces of cosmic defects or hints that inflation left non-standard signatures. Many of these searches run into a fundamental limit called cosmic variance, which is the simple fact that we have only one universe to observe. So some patterns can look unusual by chance. Even so, the measurements are sharp enough to place strong bounds on many exotic possibilities. This is one of the most fascinating aspects of modern cosmology. It can test ideas about the first instance using faint patterns spread across the entire sky. The universe becomes a precision instrument, and we become its careful readers. When a tiny departure is claimed, the community demands overwhelming evidence, because small anomalies can teach us everything or nothing at all. The Big Bang model is silent about what happened before time began. When people ask what came before, they are asking a very human question, and physics answers with a careful pause. The Big Bang model describes how the universe evolves from an early, hot, dense state. It does not automatically provide a chapter titled Earlier Than Time, because in many versions of the story, time itself is part of what emerges. In that case, before is not a place you can point to. because the meaning of before depends on time already existing. That does not mean curiosity is unwelcome. It means the question pushes us toward the boundary where our current theories stop being reliable. To go further, scientists look for a deeper framework that can describe the earliest instance without breaking down. Until then, the model stays honest. It tells us what it can, and it refuses to invent what it cannot test. Some proposals replace a beginning with a bounce from contraction. One alternative picture imagines a universe that was once shrinking, then reached a turning point, then began expanding. In this view, the Big Bang is not the absolute start. It is the moment the direction changed. The appeal is that it might avoid an initial singularity, and it might offer a natural explanation for why the universe looks so smooth on large scales. The hard part is the bounce itself. At extremely high densities, ordinary physics may not be enough. So, these models often rely on quantum gravity effects that are still being developed. They also face a memory problem. If a prior universe existed, what information could survive the crushing contraction, and what would be erased? Researchers look for telltale patterns that a bounce might imprint on primordial fluctuations, because a viable idea must offer predictions, not only a different story. It is a daring possibility. It turns the origin into a transition, and it asks the cosmos to be cyclic rather than one time. Other proposals suggest inflation continues elsewhere, creating many bubble universes. In some versions of inflation, the rapid expansion does not end everywhere at once. It ends in pockets like raindrops, forming in a cooling cloud, while the larger inflating space keeps expanding. Each pocket can become a universe region with its own hot start, while other regions remain in the inflating state. These pockets are often described as bubble universes, and the wider inflating background is sometimes called eternal inflation. The idea is dramatic because it reframes our universe as one region among many, rather than the whole show. It also offers a potential explanation for why conditions in our universe seem tuned to allow complex structures. If there are many bubbles with different effective properties, then some may naturally be more hospitable than others. The challenge is evidence. If other bubbles exist, they may be causally disconnected from us. Scientists therefore look for indirect signatures, such as subtle scars that a past bubble collision might leave in cosmic background patterns. It is speculative, but it is not casual. It lives or dies by whether it can be tested. Multiverse ideas are controversial because they can be hard to test. Science thrives on predictions you can check. So the multiverse raises a sharp question. If other universes exist beyond our observable horizon, how could we ever gather evidence? That is where the controversy lives. Some researchers argue that if a theory which is otherwise well supported implies a multiverse, then the multiverse is part of the package, even if direct tests are limited. Others argue that an idea becomes scientifically fragile when it can explain almost anything after the fact. The debate is not only philosophical, it influences how people choose models, what counts as an explanation, and what kinds of evidence are considered acceptable. There are also middle paths. Some multiverse scenarios might leave traces, such as collision signatures or statistical predictions about certain parameters. Those would bring the idea back into the realm of measurement. For now, it remains a frontier where physics, inference, and humility meet. It invites wonder, and it demands rigor.
The earliest fraction of a second is beyond current direct observation. We can see the universe back to when it became transparent to light, and we can infer earlier conditions through relics like element abundances and background patterns. Still, there is a curtain we cannot lift with present tools. The earliest instance was so energetic that our best tested theories are pushed to their limits, and we do not yet have a complete, verified theory of quantum gravity to guide us there. That is why cosmologists treat the first tiny slice of time as a place of informed conjecture, not settled fact. Yet it is not an empty canvas. Particle physics sets limits, and observations narrow what could have occurred, because later evidence has to remain consistent. Scientists use this method much like archaeology. You cannot witness the earliest moment directly, but you can examine what it left behind and eliminate scenarios that would have produced a universe unlike the one we observe. The boundary is real, but it is not the end of understanding. It marks the beginning of the most difficult questions. Even so, the later fingerprints are clearly visible in light, elements, and structure. Even if the first moments are hidden, the universe left a trail that becomes easier to read as it evolves. Ancient light carries patterns from early conditions, preserved across the entire sky. The mixture of the lightest elements records nuclear reactions that took place when the universe was young enough for the entire cosmos to behave like a reactor. The arrangement of galaxies shows how tiny early differences grew under gravity into filaments, clusters, and voids. These are not separate narratives. They are cross-checks that link different eras together. If you change the early conditions, you change what the later fingerprints must look like. That is why modern cosmology feels so compelling. It is not based on a single clue. It is built from independent records that must agree. When they do, the universe becomes a coherent narrative rather than a collection of mysteries. We cannot watch the beginning directly, but the universe has been leaving evidence ever since. The universe is expanding now, and it will keep changing for eons. Expansion is not only a historical event, it is the present tense of the cosmos. Distances between faraway galaxy groups continue to increase, and the rate of that increase is shaped by the universe's contents. Over immense time, expansion changes what kinds of interactions are common. It affects how often galaxies collide, how easily matter can gather into new structures, and how the cosmic web evolves. The future depends on what drives the expansion. If acceleration continues, the largest scale structure will gradually freeze out, with fewer new connections forming between distant regions. Locally, though, gravity will keep crafting its own stories. Bound systems can continue to orbit, merge, and form stars until their fuel runs low. This is one of the strangest truths to sit with. The Big Bang is not only about a beginning, it is about a universe that is still unfolding, still stretching, still aging, and still turning its initial conditions into a long, slow future. Far future galaxies may disappear from view as horizons grow. If cosmic acceleration persists, there is a quiet consequence that feels almost poetic. Light from very distant galaxies may never reach us, not because it stops being emitted, but because the space it must cross grows too quickly. Over enough time, more galaxies slip beyond a cosmic event horizon, and their signals fade away from our reachable universe. Observers in the far future could look up and see a much emptier sky than we see now. They might not detect the cosmic background easily either, because it would be stretched to much longer wavelengths and become harder to measure against local noise. That future emptiness would not mean those galaxies ceased to exist. It would mean the observable universe shrank in practice, even while the universe itself kept expanding. This idea changes how you think about astronomy. We live at a time when the evidence for cosmic history is still visible across vast distances. The universe is generous now in a way it may not be forever. One day, our night sky could look emptier because of accelerated expansion. Imagine a civilization that arises trillions of years from now in a bound galaxy group. From their perspective, the wider universe could be almost invisible. The nearest external galaxies would have slipped away beyond the horizon, leaving only local stars and remnants.
Without a rich field of distant galaxies, it would be harder to infer expansion.
Without an easily detectable cosmic background, it would be harder to reconstruct a hot early phase. They might still do physics brilliantly, but their cosmic evidence would be thinner. This is not only a speculation about the far future, it is a reminder about timing. Our current epoch is special in an observational sense because we can still see deep into cosmic history and map large-scale structure across enormous volumes. The accelerating universe may eventually hide that grandeur from view. In that way, cosmology is partly a science of opportunity. The universe offers clues for a time, and then geometry slowly locks some of them away. The Big Bang is not only a beginning story, it is a measurement story. At its heart, this topic is about how we know what we claim to know. Cosmology takes faint signals and turns them into a timeline, a composition, and a geometry.
It does that by treating the universe as a physical system with laws that can be tested. Background light becomes a record of early conditions. Element abundances become a check on early nuclear reactions. Galaxy clustering becomes a map of growth under gravity. Each measurement has uncertainty, and each method has potential bias. So the real strength comes from agreement across different approaches. This is why the Big Bang model has endured. It makes predictions that can be checked, and it survives those checks better than its rivals. It also keeps evolving as data improves. When new measurements disagree, the model is not threatened by questions, it is sharpened by them. The story is grand, but it is built from careful listening to the sky. As we reach the end of this journey, take a moment to notice just how far we've traveled. From a universe that began hot and dense, to one threaded with galaxies, light, and time itself. We drifted through eras when atoms first formed, when darkness lingered, when the first stars ignited, and when space learned how to stretch and keep stretching. We traced how simple beginnings led to structure, how gravity shaped patterns, and how faint ancient signals still whisper their stories across the sky. All of it reminds us that the universe is not rushed. It unfolds slowly, patiently, across unimaginable spans of time. And in that vastness, there is room to let go, room to soften the day, to release the weight of thinking, and to rest inside something much larger than any single moment. If you find yourself still awake and curious, another video is waiting for you on the screen, ready to carry you gently onward. And if these quiet explorations bring you comfort, you might consider liking the video, subscribing, or leaving a thought below. It helps this little corner of calm reach others who may need it. For now, there's nowhere you need to go. Let the images fade. Let the ideas settle. Allow your breathing to slow and your thoughts to drift like distant galaxies, moving steadily outward, becoming quieter as they go. You've done enough for today. Sleep well and good night.